Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. On the 4th of May, 2022, the United States Defense Advanced Research Projects Agency, called DARPA, began seeking proposals for the development of a complete nuclear thermal rocket engine to be demonstrated in Earth orbit by 2026. This announcement did not get the attention it deserves. The United States Department of Defense had a budget for 2021 of $801 billion. To put this in perspective, you must add the budgets of China, India, the United Kingdom, Russia, France, Germany, Saudi Arabia, Japan, South Korea, Italy, Australia, Canada, Iran, Israel, and Spain, all together, to equal what the U.S. spends. That's a lot of money. To put it another way, that's 3 Elons and 1 Zuck, with more than half a Bezos left over. That's clearly enough to get the job done. And that is spent every year. And it's not like we haven't worked on nuclear thermal rockets before. Let's review what has been done, and then evaluate what will be possible once this technology is available. Nuclear power for space exploration and colonization. The most important system for successful space exploration and colonization is power. Without adequate power, you cannot survive off the Earth. There are many sources of power in space. Solar comes to mind first, but it requires very large panels to produce enough power for a large spaceship or colony. Solar will be a part of almost anything you do in space, but you need more than one source of power to be safe. The only other dependable source of continuous power is nuclear. Nuclear power comes in many technologies. We have seen fusion bombs detonated, but we can't use these massive explosions to produce usable power. It would be like throwing a hand grenade in your automobile gas tank. Lots of power, but not very usable. Let's talk about fission power. Now understand the difference between fission and fusion energy. Fission reactions split a large atom into smaller ones. These smaller atoms are more stable and have a slightly lower mass when added together than the large one did. This extra mass is converted to energy according to Einstein's equations. Note that in atomic bombs, less than 0.1% of the fissionable mass is converted into energy. It's obvious that a little fission energy can go a long way. Fusion energy is when you take 2 smaller atoms, like tritium and hydrogen, and slam them together under enormous heat and pressure so that they fuse together into a new element, helium. The sun does this with regular hydrogen all the time, but we can't create a gravity field that strong. We have to use magnetic fields in a torus. Fusion is easy to do. Getting it to produce more power than you put in is the hard part. We'll cover fusion energy in depth in another training video soon. Fission energy is definitely able to produce energy right now with current technology. 1/3 of all nuclear power in the world is generated in the United States, and some countries like France get 40% of their energy needs from nuclear fission reactors. These reactors are very large, however. We need to look at how reactors work and how to make them smaller. Luckily, brilliant people have been working on this. The Americans built the first fission reactor used in space, called the SNAP-10A. This stood for Systems Nuclear Auxiliary Power. 10A was the series number. SNAPs 3B and 9A were radioisotope thermal generators. They were not nuclear reactors as we will define them. We will get to RTGs in a moment when we talk about the MMRTG. A nuclear reactor used a chain reaction of cascading neutrons to form a radioactive element to break down other large atoms, giving off energy. It is also controllable. You can turn the reactions up or down. These reactions occur because some atoms are too large to be stable, or they have too many or not enough neutrons. There needs to be a balance between the number of neutrons and the number of protons in a nucleus. The protons all have a positive charge, and they are pushing each other apart via the electromagnetic force. The strong nuclear force acting between the quarks and the nucleons is holding the neutrons and protons to each other. The half-life of an element is the time it takes for 50% of the original mass of the radioactive element to break down. The faster an element decays, the more energy it gives off over a given period of time. But things get complicated. Uranium is the heaviest element found naturally on Earth. Uranium-238 is the most common isotope of uranium found on Earth. It has a half-life of 4.5 billion years and is not that useful as the primary fission source for nuclear reactions. Uranium-235 has 3 fewer neutrons than uranium-238, and it has a half-life of 700 million years. However, only a small percent of mined uranium is 235, and this must be separated out from the more common U-238. This requires massive, very fast centrifuges usually. As the concentration of U-235 increases, the material becomes more radioactive, and the breakdown of the U-235 can trigger breakdown of the U-238. Increasing the percentage of U-235 is called enrichment. Uranium-234's half-life is only 245,500 years, but it occurs indirectly from the decay of uranium-238 and is not easily available. Neptunium was the first transuranic element artificially created in nuclear reactors. It does not occur naturally on Earth. It has a half-life of only 2.1 days, so it would not be a good source of long-term power, as it would rapidly lose energy. Plutonium-239 has a half-life of 24,100 years and was the second artificially created element. Plutonium-239 works in atomic bombs and can be very useful for nuclear energy. Plutonium-238, with a half-life of 87.74 years, is a good source of energy and is used in radioisotope thermal generators, or RTGs. For nuclear reactors, the fuel rods usually have a zirconium outer tube containing pellets of fissionable material. These rods usually contain uranium-233, uranium-235, and plutonium-239. When these atoms are hit by a slow-moving neutron, note that a fast-moving neutron does not work. The atoms split into 2 or 3 smaller nuclei. These daughter elements can themselves be radioactive and will break down into further daughter elements until they reach a stable isotope. The final breakdown process can take thousands of years. In a reactor, the neutrons are slowed by a material placed between the fuel rods. This material is called a moderator. It helps to slow the neutrons. In many reactors, it is water. These are called light water reactors because they use regular water and not heavy water with deuterium, and account for about 75% of the world's reactors. 20% of the world's reactors use graphite as a moderator, 5% use heavy water, and a few use beryllium. The last one is of interest to us because it can be used in a very small reactor with no water supply, and it's metal. In a fast reactor, you can use plutonium-239 surrounding the core with a moderator, like beryllium. Fast reactors use a higher percentage of high-energy radioactive fuel, and they produce more uranium than they use. The extra uranium produced can feed slow reactors and result in 60% of the potential energy in the nuclear fuel being used instead of just 1%, as in a slow neutron reactor. Now let's look back at the SNAP-10A. This was a nuclear reactor made by Atomics International in 1965. It had a launch mass of 440 kilograms with shielding and was placed in an orbit with a perigee of 1,268 kilometers and an apogee of 1,317 kilometers. The mission duration was only 43 days due to a non-nuclear electrical fault. This was the world's first nuclear reactor in orbit. The SNAP-10A reactor had a compact reactor, a neutron reflector and control system, and a power conversion system. It was 39.6 centimeters long and 22.4 centimeters in diameter. It had a mass of 290 kilograms without shielding. The reactor core held 37 fuel rods. These fuel rods were made of zirconium uranium hydride. It was designed to produce 30 kilowatts of thermal or heat energy. The reflectors were made of beryllium, which bounced the neutrons back into the core, allowing more reactions to take place. The reflectors had a band holding them together under pressure with an explosive bolt attached. The bolt could be detonated, removing the reflectors and shutting down the reactor. A coolant was used to carry away heat from the reactor. In this case, it was a sodium-potassium metal alloy. The coolant was circulated through the core, then into thermoelectric converters by a liquid metal conduction pump. The thermoelectric converters contain silicon-germanium thermocouples isolated from the liquid metal by a heat exchanger. The temperature difference between the liquid metal sodium-potassium coolant and the cold of space created an electric potential and usable electricity. This thermocouple system is how most RTGs work also. The SNAP-10A reactor produced about 0.5 kilowatts of electricity. 20% of the reactor's power went to an ion engine using cesium, similar to the CERT-1 test that we talked about earlier. The reactor generated 4,500 volts at 80 milliamps to power the thruster and produced about 8.5 millinewtons. The batteries on the spacecraft would charge for 15 hours using about 10% of the output of the reactor, then fire the ion drive for less than 1 hour. They had quite a bit of electromagnetic interference on the satellite, and it suffered a failure after 43 days, possibly due to arcing. The U.S. did not really try to optimize and pursue this type of technology due to the worries about a nuclear accident spreading radioactive materials across the Earth's surface. The Soviets made a similar reactor called Topaz. It was manufactured by the State Research Institute under the Ministry of Atomic Energy. They tested Topaz 1 and 2 in space. Topaz 2 was labeled this by the Americans. It is a different design than Topaz 1 and should be called Yenisei, as the Soviets named it. Topaz was tested in 1971 by the Soviets and first flown in 1987 on the Cosmos 1818 satellite. It failed in the 1990s due to a coolant leak. The Topaz was tested for 1,300 hours and generated 5 kilowatts of power for 3 to 5 years using 12 kilograms of reactor fuel. Its mass was about 320 kilograms. Note the power of the Soviet reactor was 10 times more than the American SNAP 10A, but came almost 2 decades later. The Cosmos 1867 satellite also had one of these reactors. One operated for 6 months in space, the other for a year. The Soviet program was canceled by Mikhail Gorbachev in 1988. These reactors have active pumping systems and liquid coolant, and the failure rate seems a little high. We routinely put up solar-powered satellites that last decades. There are some space applications where solar is not suitable. Mars is about 1.5 astronomical units from the Sun. An astronomical unit is the average distance of the Earth from the Sun. This makes it easy to figure out the solar flux of power that reaches Mars. If there is 1,400 watts per square meter at the orbit of the Earth of flux, and we know that flux decreases by the distance squared, we can take 1 over 1.5 squared and get 1 over 2.25. Factoring in our 1,400 watts at Earth, we end up with 622 watts at Mars, or about 44% of the solar energy available at Earth orbit. This is enough to power a small rover, like Mars Pathfinder rover Sojourner and the Mars Exploration rover Spirit and Opportunity, but not enough for a more massive rover, like the automobile-sized Curiosity rover, currently exploring Mars, or the upcoming Perseverance, which will be very similar to Curiosity but have a drone helicopter called Ingenuity and some updated test equipment. These heavy rovers need a stronger power source, and this is where RTGs, or radioisotope thermal generators, come into use. These rovers will be using the MMRTG, or Multi-Mission Radioisotope Thermoelectric Generator, designed by Aerojet Rocketdyne and Teledyne Energy Systems. These generators use 8 plutonium-238 oxide modules for power. The plutonium oxide generates heat as it decays. This heat is used to make electricity using the thermocouples. When one end of a thermocouple is hot and the other end cold, electricity is produced. The thermocouples on the MMRTG are made from tellurium, silver, germanium, and antimony. These radioisotope thermal generators produce 125 watts of power at the start of the mission. This will fall to 100 watts after 14 years. The MMRTG nuclear battery has a mass of 45 kilograms. This gives a power density of about 2.8 watts per kilogram. Curiosity has 1 MMRTG. NASA has enough plutonium available to make 3 more. One will be used on the Mars 2020 rover, the other 2 available for other missions. So, if we want to equip our spaceship or colony with a reliable nuclear power source, do we choose this option? It would take a lot of MMRTG batteries to even power the average American home. The average American uses 28.9 kilowatt hours per day. The MMRTG can generate about 3 kilowatt hours per day. That means you would need 8 of them for the average home. Let's say you want to power a Vassimer engine at 200 kilowatts, the smallest Vassimer that's being made by Ad Astra and Dr. Chang Diaz. You will need 1,600 MMRTGs. That's not very doable since there are only 2 more available, and the mass would be 45 kilograms times 1,600, or 72,000 kilograms. So the most powerful rocket flying today, the Falcon Heavy, can only lift 63,800 kilograms. So let's look at some other options. The Topaz had a mass of 320 kilograms and produced 5 kilowatts of power. That means we would need 40 of them to power our 200 kilowatt Vassimer, and the mass would be 12,800 kilograms. That's somewhat better. The Falcon Heavy can get that into orbit with 51,000 kilograms left over for you, the rest of your spaceship, and everything else you need. But are there more powerful small reactors? The KLT-40 family of reactors used on Russian ships use 30 to 90% enriched uranium-235 fuel to produce 135 to 171 megawatts of thermal power and about 52 megawatts of electrical power. Now we are talking. These are used on Soviet ships and icebreakers and floating power stations. The KLT-40S, which can use lower enriched uranium, can produce 300 megawatt thermal power and 70 megawatts of electrical power. The core is 1.22 meters in diameter and 1.2 meters tall. It has 8 control rods plus 3 emergency rods. Control rods can be lowered into the core to slow down the reaction for less power, or withdrawn to speed it up for more. This reactor can operate for 2.3 years without refueling and has an expected lifetime of 40 years, but they use pressurized light water as a coolant and moderator and have a mass of 70.5 metric tons for the reactor vessel, not counting the water you will need or the power circuit. The power circuit alone has a mass of 23 tons. This is a total of 93.5 metric tons for the hardware, not including the water. Once again, we have exceeded the Falcon Heavy, and even the Starship is only projected to get 100 tons into orbit. The only rocket that could have gotten 130 tons into orbit was the Saturn V. Our only hope of getting something this massive into space and we threw it away. The SLS Block 1 can only get 95 tons into orbit. Don't get me started. Block 2 is supposed to get 130 tons into orbit. Yay! After only about 70 years, we will have matched the technological accomplishments of our grandparents. Progress is wonderful. What else is available? The Russians have also made a tiny 12 megawatt electric and 62 megawatt thermal reactor called the EPG-6. This is the smallest reactor in operation in the world. These were built in 1974 and started being retired in 2019. Pretty good durability record. I can't find a mass for it, but let's be crazy and say that if the KLT-40S has a mass of 93 tons and produced 300 megawatt thermal, so its mass is 25 times more than the EPG-6, that this little guy pictured here could have a mass of, let's assume, the same ratio, 1 to 25, giving us 3.72 tons. Let's up that to 10 tons for power generation and advanced cooling equipment. So for 10 tons of mass, we get 12 megawatts electric and 62 megawatts thermal. Now we have plenty of heat and electricity for our moon base. In fact, the EPG-6 was made for an extreme environment. It was used at a power station in northern Siberia above the Arctic Circle. It was too expensive and difficult to pipe or truck hydrocarbon-based fuel up there. So we will use this excellent little built and proven reactor type with modifications to power our lunar base, Aldrin cycler, or deep space exploration vessel. We'll look at other forms of power generation soon and build a potential true spaceship, one capable of having adequate shielding, thrust, artificial gravity, and everything else you need for a real spaceship or colony. Now let me make clear, a lot of people are scared of plutonium. But the plutonium used for RTGs, plutonium-238, cannot be used to make an atomic bomb. That takes plutonium-235. The heat from these devices, combined with new thermovoltaic cells, might allow solid-state nuclear power systems with about 3 times the efficiency of current models. That could power electrothermal or ion rocket engines, which we will discuss next week. Combining high-thrust nuclear thermal with high-efficiency nuclear electric or electrothermal rocket engines could save us many months on our flight from Earth to Mars. That means less in-space radiation exposure and more supplies making it to the new colony. Something to think about. Thanks for listening and stay safe at Astra Pro Terra.